translate an IP address to something else. Now, this can be done for different reasons. If you are basically sending traffic outside, outbound traffic, generally we kind of do source NAT for that. And in fact, we are using it as we speak right now. So all of you are attending this Zoom call, is this Zoom meeting. So a packet is going from your laptop, hitting your home broadband router. If your router looks at the source IP in the packet, that's your laptop's private IP actually. So what your router is doing is basically replacing that source private IP to a public IP given on your laptop on your router's WAN interface by your ISP, and then shooting that packet onto the internet. So the Zoom server is actually getting that packet, and it is seeing the WAN IP of your router as a source IP. And when the Zoom server is going to respond back, it's going to respond back to the WAN IP of your router. And when the packet comes back all the way back to your router will say, okay, let's replace the destination IP on this packet and put your laptop's IP back into that. That's fundamentally for inbound traffic is where we do DNAT. So we are kind of using it as even now as we speak. So NAT in general is a stateful activity. So routers do maintain a NAT table because it's connection based. So it's a stateful logic. So if you wish to use these two are stateful NATs. If you want to use this, your NSX T1 or T0 gateway must be running in active standby, because only in active standby we support stateful services. But if you say I'm running my T0 specifically in active, then T0 cannot do that. It cannot offer you stateful NAT. Source NAT, DNAT, nothing is possible. Stateful one. But your T0 can still offer you stateless NAT. Stateless in the sense T0 will do NATing, but it won't bother about tracking that, basically tracking that connection actually. So it's going to work more or less like an ACL logic only actually. So this is what we support if your T0 is running in active HA mode, because that's going to bring asymmetric routing. And stateful services don't really work with asymmetric routing. So then this is your only option on a T0. But if you change your T0 to work in active standby, you can do everything then, all this. We also support NAT64. So this is, yeah.
Stateless that it will use only for when we use the one-to-one NAT, it uses it. If you're using hide NAT, then in those situations it's not useful, right? It is not useful.
Yeah, it's not actually. Now, you can do one-to-one or you can do basically many-to-many also actually. So in both cases, stateless NAT can be used on a T0. If you have to do NAT on a T0, but you say that we can't be running this T0 in active standby, then that's the only option that you got actually on a T0.
No, like in normally what if you're doing hide NAT, in that case, it will have the source port, everything it will record, right? In if the while the return traffic goes to similar, it has to go means then that NAT table has to be referred. Otherwise, how the
so what you're saying, that is stateful NAT actually. Because return traffic, if it needs to go through, that means your router needs to maintain the NAT table, right?
Yes, yes.
So if you say active on a T0, it won't do that simply.
Okay.
It will simply just translate and just forget about it actually.
Okay.
So when we say NAT64, this is the other option to make an IPv6 infrastructure talk to an IPv4 infrastructure. Because generally, if you look at IPv6 and v4 are fundamentally two different protocols, they can't talk to each other directly. So unless the whole world adopts IPv6, which is not going to happen in our lifetime, till that time the only option is, if you want to make v6 and v4 infrastructure basically talk to each other, NAT64 is the only option. only logical option then. Where if you have a client, let's say sitting on a IPv6 environment, and let's say the client wants to access maybe some service on a IPv4 infrastructure. So in such a case, we will NAT that IPv6 client's communication first to an IPv4 address, and then we'll basically establish a communication to the IPv4 destination. So that way, we can still make IPv6 and v4 talk to each other. So initially, when VMware brought this functionality in 3.0 NAT64, this was mostly limited to T0 gateways. But now we do support this on T1 gateways also. And remember, this is a stateful NAT. NAT64 is stateful. So if you want to use that, whether you are configuring this on a T1 or a T0 gateway, you must ensure that gateway must run in active standby only. Otherwise, can't use that feature. So when we talk about source NAT, this is generally for outbound traffic. So here, if you see, let's say we are kind of doing a source NAT. So let's assume this is my VM IP, which is connected to an NSX network here. And I want whenever this VM wants, all I want is whenever this VM wants to communicate outside, I want my T1 to do a source NAT on this VM's packets and replace this source IP with this translated IP that I'm telling it to. So whenever the VM sends this traffic, it hits the T1 gateway. Now remember, if you want to do NAT, again, it's a service. So your gateway must have a SR, service router, because it's the SR which will do this NATing for you. DRs don't do any of that. So now once the packet reaches the T1 service router is going to replace this source IP with whatever transit IP that you have told it to, and then forward that or route that packet further. So as a result, you are basically making your web server talk outside using a different IP actually. You're basically telling your router to simply replace that IP. So the outside clients, they're going to simply see that, oh, it's 80.80.80.1, which is basically talking to us. Whereas when we talk about DNAT, this is generally for inbound traffic. So if I say on my T1, you can do this on T0 also, but the only difference is your T0 must be running an active standby if you want to do a stateful version of the NAT. So in this example, we're doing it on T1, where we're saying that if the destination IP in the packet is 80.80.80.1, then my T1 gateway should basically replace that IP address, that destination IP address, with what I'm mentioning now. Basically, my web server IP, let's assume, which is 172.16.101.11. And the DNAT is generally what is the method used to expose any services outside, actually. Like if you want to maybe expose some web server, maybe not only on the internet, but say even within your LAN infrastructure, you will normally do a DNAT for that, actually. You also have this option of configuring no source NAT or no DNAT rules. This is to explicitly define that for a specific communication, you don't want the router to do a source NAT or a DNAT. Like take an example that if you have a NAT rule which says my web segment subnet, which is 172.16.10.0/24 or something, if that is a source subnet, translate that to some other IP. So you've defined a source NAT rule like that. But then for a specific communication, you say that, hey, I don't want source NAT to happen on this communication. Now what communication? Let's say maybe one of your web servers, or basically your web servers, they send syslog messages also, so to some syslog server. So whenever my web server is talking to my syslog server, I don't want source NAT to happen on those packets. So you can create a no SNAT rule for that purpose, actually. Because if NAT happens, then obviously the syslog server will see that entry coming from a different IP then actually. Similarly, for DNAT also, you can create an explicit rule that you don't want destination NAT to happen on certain specific communications. So this is mostly relevant wherever the actual IP needs to be known. Generally, this is good for, I would say, for logging environments, maybe a logging servers. Obviously, they need to know what is the original IP, who is actually sending this as log entry. They need to know that. Or if you're talking to an authentication server, it needs to know your IP. So it's good. It's a good practice not to NAT that traffic in between actually. And then comes reflexive NAT or stateless NAT actually. So this is ideally available only. This is the only option that you got ideally on a T0 gateway if you happen to run your T0 gateway in active. Your T0 won't even show you options for stateful source NAT or DNAT. If it's running in active, it'll simply say you can only do a reflexive NAT or a stateless NAT. That's the only option that you will be provided with actually. So in this method, the stateless NAT rules are basically kind of working like ACLs, and you have to define them in both directions, for inbound also and for outbound also actually. And since the same rules are kind of configured, like if you see here, I have this T0 SR running on Edge 1 and Edge 2 in active. So since I have this stateless NAT rule configured on this T0, that means technically this rule is available on both SRs actually. So that anyway helps in asymmetric routing flows actually. So it's like saying when the traffic was coming in, it came through this Edge 1 T0 SR. So this guy NATed it, and the traffic came to this virtual machine. But when the VM is responding back, the T0DR, if you notice, T0DR will do ECMP logic actually. So as per ECMP, it can actually forward the traffic via the other T0SR also, which is running on Edge 2. So here again, that T0SR basically can NAT that traffic while it's going out, completely in a stateless manner. So they will not be bothered about basically tracking connections or basically maintaining any NAT conversion table or anything. Nothing. So where do you configure all this from? There's a NAT section in the UI. So if you go to your NSX infrastructure, okay, so if you want to do NAT, you can do that from networking. You can go to NAT, and there you have to choose your gateway first. On which gateway you want to do this actually. So see, right now my T0 is actually running in active. If you see here, it's running in active mode actually. So if I go to NAT and if I choose my T0 and I say add a NAT rule, say it only gives me reflexive NAT option, nothing else. Like even if I just say something here, this is the only option that you got because the gateway is running in active. So you can't think of doing any stateful NATing here actually. If you want that to happen, you need to change the HMO to active standby because we require symmetric routing flows actually. But if I change this to my T1, T1s don't run in active ever. They always run in active standby only. So here, if I do that, see, I can do everything. So I can do a traditional stateful source NAT, stateful DNAT. I can do a no source NAT, no DNAT. I can also do a stateless NAT if I want. So this will only come if your gateway is running an active standby. Active, the only option is reflexive NAT, nothing else. And depending upon what kind of a NAT you're trying to do, if you say I want to do a DNAT, then you define the destination IP, that if this is the destination IP in the packet, translate that into a different IP that you define here actually. And if you want to enable logging, you can do that. So here, and logging is something that you must enable. By default, nothing gets logged actually. Right? So if you say, why are we not seeing any logs? Mostly because you didn't enable logging. That's why. So here, this is the section from where you do all that configuration to create your source NAT, DNAT, reflexive NAT, all that. So if you are configuring a reflexive or a stateless NAT on a T0, then you can ideally, you can say, do a one-to-one NAT, or you can do a many-to-many kind of a logic also. Like you can give a range actually, a source range and a transited range also. The only thing is the ranges must be equal in sizes. So if you have, like, say 10 IPs in source, then you should have 10 IPs in transited range also actually. And that's where we have NAT64 also. So when we say NAT64, this is a mechanism which helps us to establish connectivity between an IPv6 to a V4 infrastructure. Now, yes, IPv6 adoption is happening, but again, it's not still, I would say, completely done, and it's still going to take a lot of time because IPv6 adoption is a lot of drastic change in the infrastructure. There's a huge amount of change that you will notice actually. So that's happening, but that will happen at its own pace. But until then, you will always have some environments stuck on IPv4, some environments running on IPv6, and you would require some communication between them for obvious reasons, unless everything moves to IPv6. So till that time, the only way is to have NAT64 kind of solutions working. So if you wish to use this, now you can actually do this on T1 gateways also. Otherwise, earlier it was mostly a T0 gateway option. Now you can do it on any one of these. But make sure your gateway is running in that, because this is a stateful NAT. And this requires symmetric routing flows actually. And make sure that if you are planning to use NAT, your gateway must be configured with an edge cluster, which technically means your gateway should have an SR, service router actually. So as long as you have these basic requirements met, you should be good to go and use this functionality. So where do you do this configuration? Pretty much the same place that we just saw. It's just that you have to choose the NAT64 view of it. And here you can write your, okay, you can say NAT64 specific rules actually. Okay, I think my lab is down maybe, that's why. All right, so here you define your NAT64 rules. Again, in this example, let's say they're giving kind of a DNAT kind of a logic, where they're saying if this is the destination IPv6 network, then basically translate that into this IPv4 address. And then this translated IP will talk to whichever destination that you wish to talk to, or whichever IPv4 destination that you want to talk to actually. And you can apply these rules again on interfaces, specific interfaces of your gateway, or you can apply it on tags also. Tags is basically, if you have tagged multiple interfaces, you can actually apply the rule on the tags. As a result, the rule will get applied on those interfaces for you. So what you see here is a basic packet flow. If you intend to use NAT, remember this is a regular NAT. This is not NAT64 logic that we are showing you here. So here, what they're trying to show you is that we have two tenant infrastructures. So this is tenant A, and this tenant has his own T1. This is tenant B. He has his own specific T1. So tenant A has this VM, which has, let's say, this IP address, and that is connected to the tenant A segment and to tenant A T1. Similarly, tenant B has his own segment to which his own VM is connected. Now the point is that tenant A happens to have configured a source NAT rule actually. Tenant A has configured that, where he is saying that if my VM talks outside, and if this is the source IP in the packet, translate that IP to this as per SNAT rule. So in this example, what we are trying to see is that what if this VM of tenant A communicates to this VM of tenant B? How will that packet walk be actually? That is what we are trying to understand here. With NAT configured in between actually. So to see that, let's see that we have both VMs, both tenant VMs running on the same host. So if you notice, both tenant VMs are running on the same transport node. They're obviously connected to their own tenant specific segments and tenant specific T1s. So now this VM intends to talk to this VM actually. That's the final goal. But how does NSX handle NAT in between actually? What is the packet walk for that? So as usual, this tenant A VM sends a packet with a destination IP as 192.168.10.11, which is the other tenant VM actually. So now the packet reaches the tenant A segment. From there, the packet will reach the tenant A T1 DR within the hypervisor actually. Now the T1 DR figures out that, oh, for this particular communication or this particular IP, there is a NAT rule configured. But DRs can't do that translation because these are just packet pushers. DR is kind of a dumb component actually. It is supposed to just push packets based on the table provided to it, but it can't offer any services. So DR now has to forward this packet from the transport node to its SR actually, which is running here in the edge node actually, because it's this guy who will do the NAT. So for that purpose is where now the T1 DR on this transport node is going to take the help of the TEP and will say that, okay, I'll forward this traffic to my SR. So this is where the traffic is now moving via the T1 backplane connectivity actually between DR to SR. So the TEP is going to facilitate that movement via the TEP tunnel. And now the edge node step interface has received the traffic. It will strip the encapsulation and deliver the traffic to the T1 service router inside the edge. So here it's the T1 service router, which is now going to do a source NAT translation on the packet. And it will manipulate the source IP and put the translated IP there. But then it's the T1 service router, which is going to do further routing of the packet, because eventually the destination is the tenant B VM. So now routing is going to happen from T1 SR to T0 DR over this router link. This is router link connectivity. And this is all happening inside the edge node actually. And the T0 DR is going to route the packet via the other router link to tenant B T1 DR. Now why DR if you say? Because tenant B in this example has not chosen a T1 service router actually. If they did, then this would go to the T1 SR actually. But in this example, they haven't gone with a T1 service router. That's why the router link is between T0 DR to tenant B T1 DR. Whereas if you see for tenant A, the router link is between T0 DR to T1 SR actually. So now the packet is going to be routed from via the T0 gateway over this router link to the tenant B T1 DR. And once he gets the packet, he has to now deliver the packet to this guy here. Now, in order to do that, he will first route the packet because he has a connect interface on this green segment. For him, this broad segment is a directly connected network actually for this T1 DR. So he knows how to route that. So he will route the packet. But since the VM is on a different transport node, it's going to deliver the packet to the TEP saying that, okay, routing is done. You just do the L2 delivery of the packet to that VM. And TEP, as usual, will take the packet, send that to the TEP tunnel, deliver the packet to the TEP of the other transport node. He will strip the encapsulation and deliver that straight away to that VM. Yeah. So in this case, since there was a source NAT rule configured, the packet had to come to this T1 service router on the edge, get NATed, and then get further routed via the edge, and then go back to the same transport node. So if you look at the overall packet walk, packet came from transport node A, went to the edge node, got routed here, and then went back to transport node A. Okay. So this is, yes, it's creating a routing hairpin bend, but that is the only way, because if you want NATing, SRs would be required, and SRs only run on the edge node actually. There's no other way.
Hi, Shekhar.
Yeah.
So you said for multi-tenancy from one tenant to other tenant, the communication will not happen by default. So in this case, on the T0, we need to configure any routing for this T1 for the tenant 1 to communicate with the tenant 2.
In this case, see, in this example, they haven't used VRFs actually. Right. So tenant T1s are connected directly to T0. Okay. Right. So that's why it's working. If there was VRFs employed, then yes, you would have to configure routing. So now the same packet is just going back to that particular node actually. So now if you look at the complete packet walk, it came like this. It went to T1. This guy sent it to the TEP. TEP delivered it here. SR did NATing, routed that to T0. T0 routed that to the other tenant. This guy did routing to his own network. But then for final delivery of the packet, he sent the packet to the TEP. And then the packet came back all the way and then got delivered like this actually. But in this case, imagine if there was no service router for the tenant A also, no source NAT also for the tenant A. How do you think this packet would have moved otherwise? If this VM had to talk to this VM and none of the tenants basically had a T1 SR assumed. So how did this how would this packet would have moved actually in that case? Do you think the packet would have to go to the edge node in that case? If there was no T1 service router for any of the tenants?
Yes, because the connectivity is not connected, right?
Mm-hmm.
The connectivity between different T1 is via T0 only, right?
So I'm saying if both tenants had only T1 DR created, right?
Yeah, directly via T1 DR, it will connect to the T0 DR, then it will come back.
So if you connected this T0 DRs directly to T1 DRs to this T0 DR directly, assume, don't you think this T0 DR will be here also then?
Yeah, correct.
Right.
Yeah, I meant to say it will go to T0 and it will come back.
So basically it will remain within the host only.
Yeah.
Right.
One scenario. See what happens. I have a service SR created for T1. Okay. But for some scenario, I'm not using the NAT. Okay, maybe no-NAT I'm using for this particular traffic. Okay, that information, it will be then DR, or only it have, even for that it has to go to SR?
See, if you created a service router for a T1, and even if you don't use a single service also, the traffic still has to go from DR to SR only. There is no other way. So there is no question of bypassing the SR. Even if you say I did not configure DHCP, I did not configure NAT, I did not configure anything on my T1, but I just created a T1 SR, the traffic will still actually go in this way only. Like even in our example that we just spoke about, assume.
No, only for load balancing. Okay, yeah, I agree that. But it's again, it will be flow, right? Because even for load balancing, if I configure and I need to connect between these two, so I'm not using NAT or anything. So these two, again, it will go to the edge node, again, it will come back. That will happen still to the same, right? There's no difference.
Yes. A load balancer, anyway, you need an SR then.
Yeah, but not for this particular communication, it's not being used. But
see, but you're basically you're not considering this point where if you say that I have tenant A, tenant B, assume these are T1s. So assume this is tenant A T1 DR. Same thing, this is for tenant B actually. So now, if tenant A has chosen to go with a SR, but tenant B did not. So if you look at, this is how your connectivity would be. This would be your T0. And that's your T0 SR. So NSX will configure the transit backplane connectivity here. And this is where the router link will come down. Whereas for this guy, since there is no SR, there is no transit backplane. You will have a direct router link here. So now assume if that there is a tenant network here and a tenant network here. So now assume there is a machine here on tenant A and there's a machine here on tenant B actually. And they want to talk to each other. And we haven't configured anything, no NAT, nothing, no load balancer, nothing actually. How do you think the traffic will move?
Yeah, obviously, DR to SR, then DR, then.
So
I
now,
guess we will go to edge cluster. It will go there and it will come back.
Right. So in any case, as long as you have an SR, traffic has to go to the edge. Whether you use services or not, that's a different story. If you have created an SR, traffic will go from the transport node to the edge. Okay. Because of this transit backplane.
Yes.
So that's why if you don't have maybe a use case right now for any services, or maybe if you don't have any plans of any services on a T1, don't create an SR just for the sake of creating one actually. Because you can always create it back later on actually. Because this will actually have a very big impact on your routing.
No, okay, currently for existing one scenario, I haven't created a SR. Okay, maybe in future, suddenly I just created, I'll go to the, this one, T0 or T1, I'll go to T1 and I'll just select the way it should be there. I'll just select my edge cluster.
Hmm.
Okay, in that whether will we have any impact on the like ongoing traffic or
See, the only change you will notice is like right now, for example, assume this is the router link.
no, I agree. Physically, it will connect, but either it's like without non-impacting, it will be a impacting change or
There could be a slight, I would say, brief outage for ARP actually, because your router link interface will change
yeah.
from DR to
No,
SR,
yeah,
right?
hardly one packet, two packet. That's okay.
At
But
best,
like it
nothing
will
more
be
than that.
okay. Yeah, that's a normal convergence. Fine, I agree that. Apart from that, there will be no major.
No major disruptions apart from that.
Okay.
And so that's why, or maybe if you know, or maybe if you have applications which are like maybe too picky or too sensitive, maybe schedule a time if you wish to do something, some change like this actually then.
Yeah.
But generally speaking, it won't be any major outage or anything. It'll be maybe just a convergence outage actually. All right, so let's look at that's kind of NAT. You can do a lab on that. So it will show you how do we do it in NSX.